Hi. Yes, my name is Fatima, and I'm at the Julius Sands Lab at the Montreal Heart Institute at Université de Montréal. So I'm here to talk to you about our work on refinement of SARS-CoV-2 Intra-host dataset using explainable representation. So first about SARS-CoV-2 evolution. So it is an RNA virus that is responsible for the pandemic that we know a little too well. And throughout this pandemic, this virus has evolved into multiple variants of concerns, as we know, Alpha, Delta, and more recently, Omicron. These variants evolved by accumulating mutations, and specifically during the intra-host infection, where they accumulate mutations during replication, and there's selection happening on these mutations. And the advantage, the uniqueness of this pandemic is the number of data generated. For example, across the world and across time, these infections were collected and RNA-seq libraries were generated representing these infections. These RNA-seq libraries will contain two types of mutations: consensus mutations, which are mutations that define these lineages, and will be in consensus sequences. So a consensus sequence is a sequence that summarizes the RNA-seq library. We also will find de novo mutations. These are the new mutations that happen during the infections, and these mutations are not represented in these consensus sequences, however, are important to understand the intra-host evolution of viruses. Fortunately, these raw datasets are available through the NCBI database, which leads me to our two aims that I will be discussing throughout this presentation. The first one is to develop a workflow to extract these de novo mutations using the pandemic-wide SARS-CoV-2 RNA-seq dataset. And the second aim is to investigate these de novo mutations to understand the intra-host diversity and evolution, and specifically if it's variant specific. So as I talked about the diverse data set, this is a representation in our data set. So we have a representation across time, geographic regions, and sequencing centers. So we start our workflow with downloading this data set, and we have a bioinformatics workflow that processes these libraries by mapping, quality trimming, and quality control, whole genome quality control. At the end of this workflow, we'll have a set of high quality data sets that we call mutations on, and we put these data sets into a matrix. This matrix will contain libraries as rows and genomic positions as columns, and it is encoded using the alternative allele frequency within each library. To be able to represent this data set, to be able to visualize this data set, we create this two-dimensional representation where each library is a point. So the method that we use to be able to see this, to visualize this data is called FATE, and it is best at revealing the branching structure of the data. So what does our data look like when we put it into two-dimension using FATE? And we can see each library is a point here, and we can see already some clustering structure. What does explain this clustering structure is lineages when we label by lineages. This is a qualitative visualization where we see clustering structure by lineages, and we start to quantify this clustering structure. How do we quantify this clustering structure? Is we develop this post hoc PNN metric. So if we go back to this example where each point is a library, and what we do is that we use a KNN approach to quantify the number. For each point, we quantify the number of nearest neighbor that have the same label, and we measure and then we quantify that for the whole representation by taking the mean. For this example, because it's very well clustered representation, it's at 100%. We also have a baseline value that is the PNN value that we expect at random. Here we have three labels, meaning we have a baseline value of 33%. So what does the value of the clustering structure by lineage for our data is 95%, meaning that this in this representation our points cluster at 95% using at 95% using the lineage labels. However, as we talked about, that consensus sequences are the consensus mutations are the mutations that will drive this lineage structure. However, we are interested in the de novo mutations. So we remove the de novo mutations and we redo our representation, and we can see qualitatively there's a reduction of this clustering structure, but we can also measure this reduction in clustering structure from previously being 95% to 56%, meaning there's some structure by lineage, but there's other drivers. What we looked at is sequencing center. So here, each point, instead of labeling by lineage, we labeled them by the sequencing center. Hence, the advantage of our data set that is geographically diverse. And we can see that it clusters. We can measure that it clusters by sequencing center at 63%. This shows a widespread sequencing center batch effect, and shows that errors are sequencing center specific. So we sought to identify the source of these errors and fix them. One of the types of errors we identify is low frequency. For example, this mutation here, even though it's in a very well covered region, it has only one evidence for a mutation. Another type of mutation that we looked at is a strand-specific errors. If this is when there is only one. This is when an error happens and it's only amplified by one sense. So to tackle these two types of errors, we use two metrics. So the alternative allele frequency, which is a common filter, and the strand bias likelihood metric, which is a metric that we developed to be able to identify these strand-specific errors. We also have additional steps, which basically removes extreme cases of either mutations or libraries. So what does our clean data look like? So we go back to our matrix, remove these errors, and we now have a clean data set with a PNN value by sequencing center of 21%, which is very close to the baseline level. So we can go back to our question, are mutations lineage specific? The same representation, this time labeled by lineage, and we can see there is the PNN by lineage value is also very close to baseline, meaning actually these mutations are not lineage specific, but instead it was a confounder with sequencing center. Now we have a set of clean de novo mutations, almost 400, a little bit over 300,000 de novo mutations. And of course, I'm not going to leave you here without at least one analysis of this clean data set. So we took these de novo ISNVs and labeled them with a fitness score. This is a fitness score developed by Bloom and Naher, which represent how often these mutations happen in the phylogenetic tree. And we annotated all our mutations with this fitness score, where -6 means the mutation is deleterious, 0 is neutral, and 6 has a selective advantage. So we take all our mutations, divide them by de novo ISNVs and consensus ISNVs, and within each category, we divide them by the amino acid change impact. we'll find, for example, synonymous mutations that have no change on the amino acid, which are mostly neutral, and we'll see the ones that have an impact on the amino acid change being deleterious, with stop gained being even more deleterious. And this shows that the intra-host mutations undergo strong purifying selection. We'll also notice some mutations that are interesting. These are mutations that are still happening intra-host and that still needs to be under investigation. So our clean data set has also been used in other studies in our lab. We've compared, for example, intra-host mutations to understand the selective pressures of immune evasion in SARS-CoV-2. We looked at how we compared long infections to our short infection data set, and we also more recently looked at the impact of these de novo mutations on the epitope loss. So we'll leave you with some messages. I think I showed the importance of data sharing. The pandemic was very important at sharing. Was very important at showing how we can share the data and everyone can use data, but quality is something that we need to pay attention to, and I think it was also highlighted in the keynote speaker yesterday. We also show application of representation learning, and the generation of this number of data set is important for this. But also explainability, even with a simple method that I showed you today, it is important to quantify the representation that we are looking at. And finally, I'm leaving you with a clean data set of intra-host diversity, but also the importance of looking at intra-host diversity in viral infections. I would like to thank my lab for their support and of course, I'm stopping here. I would like to thank my lab for their support and listening to me so many times, but also the award, the COSI Award Travel Fellowship, and you for listening to me. You'll find more details about this work through this QR code, and please look at other amazing work from our lab in posters.
I can start. I have a question. You talked about mutations in different lineages. Have you also quantified, or how do you deal with indels and structural variants?
Yes. Yes. So indels and structural variants were actually not included part of this workflow, but it's something that we are working on adding.